Hello. So to begin off with, what is needed to solve this is that uh, acceleration, even as a function of time, is the time derivative of velocity. So with not high-level calculus at all, you can separate your variables that way and separate into dv is equal to our time function acceleration times t, and you would integrate both sides. Now, this is where the fun, quote unquote, will begin because the one side is going to be integrated from v naught, I can't draw that very well, to the velocity at any time t. Now, if you have your bounds written like that as v of t and v naught, then in the same sense, we also need to have this side written as if that was evaluated from v at time 0, and this is the time side. This one has to be from any time of 0 to some time t. I know professors and teachers sometimes find things uncomfortable where the variable that you're integrating with here is also up in your bounds. There's nothing illegal about it in doing that. Some teachers just draw uncomfortable feelings about that. So after the integration, you'd get the following. You'd have dv just integrates to v, and evaluate on the bounds v of t to from v of 0 to v of t. So that turns into vt minus v of 0. Other side, you'd have to be evaluating an integral of time is 0. I'm trying to just fill this integral in so that it has no missing parts. For you, you'd have to be integrating 2t plus 9 t. Sorry, it takes a minute to type in this. It's not the same format as what I've handled on other applications. So that will be able to simplify to t squared plus 9t. That is going to be evaluated on the bounds of 0 to t. You can prove these that integral of t is 1/2 t squared through power rule, but there was already a 2 on it. 2 times 1/2 made the 1 on t squared. And sort of like dv, if you integrate just a constant, you get 9t, but then evaluate on the bounds. So we still have to do that. Evaluate it from 0 to t, which really, in the simplest sense, is you plug in your top bound, t, which just gives back out these. Then you plug in your bottom bound, 0, which also pops out 0 on them, because 0 squared 0, and 9 times 0 is also 0. So really, all you're left with is just the standalone t squared plus 9t equals vt minus v naught. So as a final statement, at any time t, the velocity can be described as t squared plus 9t plus v of 0. Some people that I've seen in practice do a indefinite integral and then say, oh, it's a constant of proportionality, some plus c, and then at time 0 you plug in your values and you can determine it. This is a straightforward attack to get it right out of the gate. There's no beating around it to get to that solution, and it is then we must work with now that velocity is the time derivative of your position, s. So similar steps are going to be followed. You integrate both sides. The dt goes onto the v of t now, ds goes there, and we'll end up having ds equaling t dt. And those will have their own integration bounds that'll be from s of 0 to s of t. Ooh, my handwriting with the mouse is very bad. And just like before with the v of 0 to v of t, this will be from 0 to t, which I forgot to mention. This one turns into minus 2. That's kind of important to this next step, because we're going to be integrating that from 0 to t squared using power rule integrates to 1/3 t cubed, and then power rule again, t squared integrates to 9/2 t squared, and then integrating the constant makes it minus 2t. The opposite side of the equation is going to have s of t minus s of 0. Now I would, or yes, there is a value for that. So you'd add that to the other side. At this point, you can also replace s of 0 with the value that's given in the prompt. S of 0 is 5. We can say that our s of t is equal to 1/3 t cubed plus 9/2 t squared minus 2t plus 5. Now, I did leave out that you would you'd have to evaluate this one on the bounds 0 to t, just like the last time. The last time, if you evaluate it, it will go out that way. And I hope that explained that step by step. Solved for you.